Hello, everyone, and welcome to today's webinar. We have a very exciting topic for today. It's going to be truly exciting. You see a lot of people have joined in already. Just a few technical notes. If you have any questions during the webinar, you can use the chat function on your window to ask us anything during the webinar. And my role today is being the host, so hopefully I can try to gather up on some of the interesting questions that come along. Other than that, we have some people on the chat ready to answer some of your questions, and we have a few handouts today related to this topic. But without further ado, let's get started with this. It's a huge topic.
For sure.
So I mean, today I have with me Joachim, who's a senior fluid mechanic specialist here at Aerotac. He has over a decade of experience in computer or computational fluid dynamics. A tough word for
Yes.
sure. And he's got tons of experience, and over the latest years, you've been working with CFD in the GXP industries and seeing how those two fields can overlap. And I think that's going to go for a very interesting topic for today's talk. And again, if you're having any problems with the audio or video, please write in the chat so we can fix it as soon as possible. But I think today is going to be truly exciting. It's a relatively new thing to use CFD in pharma, and
I would say so.
Well, you can see the ball start rolling now. More and more companies are trying to adapt this, and hopefully today we can get a little sneak peek into some of the benefits, the downfalls, what should we be concerned about, where should your area of focus be on CFD in pharma, right?
Yes, for sure. Thanks for having me, Jacob.
Yeah, absolutely.
It's a pleasure to be here,
Yeah.
and very excited about this afternoon or morning, depending on where you are listening in from. But I think it's going to be great to have a small discussion today, and just to introduce you to the topic of virtual temperature mapping. Maybe some of you have heard about it before. Maybe some of you it's a new topic. So
yeah, absolutely. I mean, first of all, I think we should get started with the first poll here. So we'll just get that rolling. It would be wonderful to see how many of you have any experience with virtual temperature mapping. So if you could answer the poll along here, I think we'll just start out with getting the introduction and agenda going. I'll be your host for this, so it will mainly be you talking. You're the expert.
Yes, I'll give it a go for this webinar, and then we'll take the questions as we go along. But the agenda of today is we're going to touch a little bit about sort of the current mapping process, some of the pains that some of you are familiar with. Then we'll go into a little short crash course on what is CFD. What are the three letters? What does it stand for?
Yeah.
And then we will transition into this concept of virtual temperature mapping. What are the steps? And lastly, we'll finish off with a summary of the benefits and the pitfalls.
Absolutely, that sounds great. I mean, just to get an idea of how familiar are people with it, I think this that speaks a clear language, right? It's something that there's a lot of need for knowledge about for certain this topic. So hopefully today we can get a little more insights into those things. But what's the mapping process?
What's the mapping process? So currently, when you're doing a temperature mapping, what you have seen before is that we are doing these. Let me see if we can get this. Some of the pains that you may experience is that when you're doing your PVM of your warehouse, it takes time to fill up with these dummy goods. Whether you're using cardboard boxes, plastic wrapping, then it takes time. And the larger the warehouse, well, the longer time it takes. So that's time consuming, and we can avoid that with the virtual temperature mapping, which I'll touch upon later. And that's one of the current pains. There's also, and I think some of you have seen this before, where you build your warehouse, your GXP area, and then you go to your summer or winter mapping, and then you may see a non-compliance or temperature excursion. And maybe it's because you didn't dimension, or the people who designed the ventilation system didn't dimension it correctly. Well, that would be nice to know in advance. And of course, there's been some calculations going into it. But it's always nice to see if you can sort of get an idea about where do you have your hot and cold spots, even before you set up any probes. So that's another one that we can also touch upon later. And then finally, some of you, when you are doing your GXP areas and it's been shown to be compliant, then due to logistics reason, you may want to change the layout.
Yeah.
So maybe you want to put up a rack in a different place, or you want to change where you have sort of your goods coming in. And that can be a difficult process, because then you need to decide, well, what do I do about my GXP area? Should I do a remapping? Should I wait until the biannual qualification when that's done again? And there it would be nice sometimes to get an idea about what impact does this make, because sometimes it's a small impact where it's only moving one pallet 5 centimeters, and sometimes it's 5 racks that we are moving. And what about those in between? That's something we see a lot in the current pharma that we are dealing with.
Makes a lot of sense.
Yeah.
Definitely pains we've heard about before, that's for sure.
Exactly. If we then talk a little bit about this concept of CFD, so computational fluid dynamics, or abbreviated to CFD, what we're going to do today is we're going to start talking about the last 2 words, so fluid dynamics. What is that? And then we'll transition into sort of the combination of the 3, the computational fluid dynamics. So if we start with the first 2, or the last 2, fluid dynamics is something we see in everyday life all the time. So right now, the blood is flowing through our veins. There's air in the room that we are sitting in. We also have, for example, for your clean rooms in your warehouses, you have particles that are going around. You have humidity. So a lot of different things that is involved with the movement of either liquids or gases. So that's sort of the fluid dynamics part. Then if we look at computational fluid dynamics, that is where we are trying to predict how the fluid or the liquid or the gases are going to behave, where they're going to move, what are the sort of the temperatures, and how does that, when you, for example, have your a summer scenario, then you may have a very warm outdoor environment that's going to affect your buoyancy forces, and that's something we can represent in a virtual model. So we're using, and that's where the word computational comes in. We are using mathematical equations to represent some physical laws. And I typically say that we are sort of modeling the things we cannot see with the naked eye. And that's also what we are showing here on the slide, some nice what we call streamlines, so indications of we are injecting air into a room. How does that cool down? How does that warm up? Where does it go? Do we cover all the corners in the room? That's something we can do with our virtual model.
Makes sense. So I guess also to if I understand you correctly, it's really about applying some physical laws that you have a general understanding of how fluids work through hundreds of years of experiments, and then trying to replicate that in a computer model.
Exactly. And CFD is something that was developed many years ago, and the equations that we will see later, they are from many decades ago when they were first derived. And it's something that's used in all different sectors across the globe, whether that's from the automotive to pharma. And we saw that some of you have maybe heard about virtual mapping before. There was also, I think, maybe a question later on if they have seen sort of the CFD or virtual model applied in the early stages. But now when we are talking validation, what happens there? So it's a common method that we are now seeing in different applications.
Very interesting.
If we then talk a little bit more as an example, we have here shown a sphere, and whether that's your golf ball or football at home that you're kicking into the air, you will have air coming over. What we're doing in the virtual model is that we are then dividing the air up to some small centicubes or some small, we call them mesh cells. So you can imagine that it's a very small volume that sort of represents the air within that region. And then for all these small cubes, we are solving these mathematical equations that, let's see if we can, that are called the Navier-Stokes and the conservation of mass. And that is those that represent these physical laws and have been there for many decades. We put that into our computer. We have a supercomputer that we are using.
It's not run on your small laptop at home.
Definitely not. What we're sitting with here it's many times more powerful. And you can also imagine that, for example, for warehouses, we have many millions and millions of cells.
So if we're talking a warehouse, for example, how large are these cells we're talking about?
It depends a little on the side, but typically it goes everything from a few millimeters to maybe 1 or 2 centimeters.
Okay, so it is really a lot of small cubes that you have to account for.
Exactly.
Okay.
And then we use some commercially available CFD software to solve our equations. And then we can get an indication of what is then the virtual or the flow field that we will see behind this sphere. And similar, we can do it for a warehouse or another GXP area. So that is sort of the process. So you are starting with your a representation of your physical element. You're representing that in your virtual model, and then you're solving these equations, and then you'll put it into a very powerful computer, and out you will get some indications of some flow fields and temperature and humidity.
So you actually need both the physical model of how your warehouse looks like and all the external forces or external temperatures and energy transformation, and you do all of that and transfer it into computer actually.
Exactly.
Okay.
So there's quite some input going into it, and then we can also get a lot of output from it. If we then talk on what is sort of CFD within pharma, has this been used before? What we see is that these virtual simulations or mappings have actually been used in these early stage flow concepts. So whether you are considering if you should have nozzles that are shooting down, or whether you should have sort of a fabric air duct design, that gives different flow fields and thereby also different temperature fields. So that's something you can do in your virtual model. We have also seen that, and some of you are recognizing this, where you put in your heat loads and you represent a worst case condition. Then you can actually use the CFD model to predict whether you should, which size of air handling unit you should put in, or where should I put my racks.
So it's correctly understood that these two first concepts of very early stage design and also trying to evaluate the designs you have, those have been in use for a relatively long time, right?
Yes.
That's not something new per se.
No, no, exactly. And that's what we have done for many decades. And I think that's a good transition into the third element, or the third sort of step on that staircase, and that is the validation and mapping. So now everything up until the second point, we didn't really compare anything to physical measurements, but now we're actually using virtual models to support and in also some cases replace physical experiments and also mappings. So I think that's a really interesting sort of step, that we're no longer just using it in the early stage, but we are actually also, and it's not replacing all of it, it's supporting and then only substituting some elements. Because we still need the real world to make sure that we are, we know what we're doing and we are factual.
And why do you think that the first two stages have been, performed in decades, and only within the last few years we're starting to see it move into the validation and mapping?
So I think that's a great question because in recent years we have seen bigger and bigger computers. We can divide these warehouses up into even smaller cells,
Yeah.
and thereby capture a lot more of the physics that's going on. So I think that's why partly we have not seen this transition until now.
Yeah.
And then also we need to have confidence in what we are doing.
Yeah.
We can't just and CFD, some also call it colors for directors, because you can get some really nice colors, but it's really key here that we get the right colors, because you can get red and blue, but in this case, especially when we're dealing with patient safety, we need to make sure that we are representative of reality. Yes. If we then go into the virtual temperature mapping, then that is sort of a new concept.
Yeah, but I think, and as a transition to that, I think we'll have our second poll for today. So basically, if you were to cut your commissioning time, how much time would you actually have to cut off the commissioning time before it could actually be interesting to you? I think that could be a very interesting topic to sort of to get your answers on. But I think while this is running, there's been some questions here along the way. First of all, I think we have a question here saying related to AI. I think so I think a derivative could be, does this have anything to do with AI?
Yeah, we do get that question every
Yeah.
now and then. AI and CFD are two different things. It's not that we are using some sort of machine intelligence to predict what the temperature field is. But of course, there are softwares now that has some AI tools and supportings. But it's still two different things.
So if I understand you correctly, where AI can sort of hallucinate and guess, CFD is pretty much based on physical laws rather than estimations of what the future might be.
Exactly.
Yeah. Okay. That's nice to get. But thank you for that question. So we're getting a little bit of different answers along here. It's 2 to 3 months. That seems interesting if we could cut that away. But pretty much across the board. If you could type in the chat how much you typically use on a commission time, I think this will be very nice to have that as a relative number to these. So I'm just gonna get this out of here and get moving. What is virtual temperature mapping? You have some more points to make here.
Exactly. Then we're transitioning to the VTM or virtual temperature mapping. We have this overview of, on the left, we have a physical temperature mapping, and then you have your virtual on the right. If we start with the physical on the left, typically we start with your OQ temperature mapping, so an empty representation of your GXP area. Then you load your warehouse with dummy goods, and whether this is cardboard boxes, plastic wrapping, covers, or whatever you may use. And depending on the size, this may take anything between 1 to 12 months. Of course, the smaller the warehouse, the less time it takes. And then you do your PQ temperature mapping, so you represent your full state. Then you document that, and then you get your authorization. The difference for the virtual temperature mapping is that we still do the same. The first step, that is your OQ temperature mapping.
And so with actual sensors in place, right? Yeah.
Exactly. Yeah. So you do your physical one with, I don't know how many loggers, anything between.
That could be a lot.
Exactly. And I think that's also the reason why the two of us are here, because you are the expert within the physical mappings, and we have some experience knowledge within the virtual mapping. So when we get the data from UPRI of a physical mapping, OQ, then we compare that to our virtual model. So this is where we assess the credibility of the virtual model. And typically we are within plus minus 0.5 to 1 degree Celsius for each of these lockers. And this is to show that we are capturing the physics in the warehouse, so that we represent the flow field, the temperature field, to the desired accuracy.
So is that, if I may ask, is that in order to verify that the model is correct, or is it to verify that there might be some physical differences between your computer model of the warehouse and the actual model or the actual physical warehouse?
Yeah, and typically when we are involved in some of the early stage design phases, I think you have all seen that the initial blueprints of a building do not always end up be seen in the actual as-built stage. So that's typically where we need to make sure that whatever has been built, we represent that in a virtual model. So that's the essence of that sort of step.
Yeah, makes good sense.
When we've then showed that our virtual model is accurate and we have validated it against the physical data, then we expose the warehouse to these seasonal variations. So this could be your worst case summer or worst case winter, and also do it for a PQ state, so a full state of the warehouse. And this is to show that the GXP area is compliant also for the extreme scenarios. We document that to the medicine agencies, and then they typically grant a first authorization. So they allow you to start using the warehouse because you have shown that your warehouse or GXP area is compliant, and then you can start using it just as you normally would.
So actually, in relation to that, we've got a question here from Francis. I think a really good question, actually. Says, it makes more sense to me to do it the other way around. Cut down OQ time by doing it virtually, and if confident, then fill the warehouse and perform PQ with sensors to actually demonstrate performance. So that's a great question. Can't you start out with doing the virtual mapping and then doing the physical mapping afterwards?
We do have virtual mappings before the physical ones. And that is typically to get an indication of where do we have hot and cold spots in the room. It can feed into where should you then position your lockers. But we still, before we can get any sort of authorization from the authorities, we need to make sure that we have compared the virtual model to physical measurements.
So basically you need both the physical measurements and the virtual model, and those need to align before you can truly trust the outcome of the virtual model, I guess. Yeah.
Exactly. Exactly.
Okay. Great question. Thank you very much.
And whether you do that for a PQ state of the warehouse or an OQ, that's up to the client. Often they want to save sort of the PQ because it's cumbersome with all these dummy goods. So that's the reason why they do the OQ.
But in theory, you could do it the other way around, saying we do the physical mapping with loading, and then validate the model, and then do the empty one in simulated. So you could imagine a scenario where someone was doing operation where it was actually the most cumbersome thing would be to remove all the goods. Then you could do it the other way around, actually.
Yes.
Okay.
Exactly. Yes.
Yeah.
Then if we share that with the authorities, we get the first authorization, and then you're allowed to start using your GXP area, and then you can load it with the real goods that you intend to use, and then later you can do your PQ temperature mapping with the real goods in place. And then that is then shared with the medicine agencies, and then you get your what we call the second authorization. So this is typically sort of the workflow. And here you can see that for the VTM, those are sort of the steps from 2 to 4, and they typically take about a month to do. And depending on the size of your warehouse, so in the virtual model, it doesn't matter how big your warehouse is. It doesn't take us longer or shorter. It's the same time. So there we see significant gains in the cutting the commissioning time for larger warehouses.
Makes sense. So just there's a follow-up question here from Francis saying, so, but then is the final PQ vertical or physical?
So the final PQ after you have loaded your warehouse with the real goods, that is a physical test. And we may also do the virtual test just to show that we didn't have the data at the time, but we show that the model is still accurate even for the PQ state. So that's sort of the checkup that can be done later in the process. This is just an overview of sort of the timeline of the typical process versus the virtual one. So I know you're the expert on this, but the WHO guideline says that you're doing your summer mapping in the OQ and the PQ. You then need to do your winter in the OQ and PQ, and then you can do the operation. Whereas in the virtual one, what we're doing is only one mapping, whether that's summer or winter, it doesn't matter. And then we do the PQ virtually, and then we start in operation.
Okay. Yeah, so the basic idea is that you can actually go into operation early on rather than having to wait for summer, winter, or rather than having to wait for filling in dummy goods.
Exactly.
Allows you to go into operation earlier, and then if you would like to, or I guess if there's any doubts, you can always do the physical whilst in operation.
Exactly.
Okay, makes a lot of sense.
So that backs it up for authorizations. We do get the question a lot: is this the first time that this has ever been done, or how many times have we successfully executed this? And we've done it on quite a few different projects now. We have done it here in Denmark for two companies called TMJ and Movianto. And then we have worked with Takeda in Belgium. And then we are also working with Novo Nordisk on some current projects. And also for other projects, we do also have one that is ongoing. And this is where we are at the end of the project, we'll submit that to the FDA to get their approval. But we have already spoken to EMA about this, and as you can see, both in Belgium and Denmark, they were actually happy about this approach because you can test your warehouse in even the most extreme scenarios, and that is not always guaranteed.
Yeah, that's a really good point, because we often get that question sometimes, like you should do seasonal variations, but it's very difficult. I think everyone who has ever tried performing summer and winter mappings, it's very hard to find, let's say, the week or the 2 weeks at the very hottest of summers and the very coldest of winters, right? You can never get exactly that.
Exactly.
So you can basically, I guess you could also foreshadow what happens with climate change. If it gets hotter or it gets colder, you can actually foreshadow what would happen. Yeah. Okay. Really
and
cool.
that we can implement into our virtual model. There's not really any limitations to that. We're not limited to the weather of the day. Whenever that's performed.
Oh, cool.
If we then go through the steps of how would you go about this, the virtual temperature mapping. First, we would gather some inputs to set up our virtual model. So whether this is blueprints of the building, a data sheet of insulation, specifications of the air handling unit, and then what is it made of? You have some insulating walls. How many racks do you have in there? That we need to gather some input in order to create an accurate virtual model.
But you also need all the way down to which door is it, and which kind of windows are there, and how they are constructed. Okay, so it's a very detailed actually input gathering.
Exactly.
Okay.
In order to be accurate, we also need to get accurate input. And there the critical part is, and we do have some experience now on what makes the most impact, and we also know who to contact within the different organizations who may have this knowledge. So that's also something we have gathered over the years. Then we create the virtual model. We can also run some preliminary simulations to get indications of the flow field. As I said before, any mappings. So even before you set up your first temperature probe, you can get an indication of where's the hot and cold spots.
That would be wonderful.
Exactly.
Rather than guessing.
Exactly. And coming up with these rationals for where do we expect it to be. Here we can actually get some pretty good insights into the expected temperature fields. Then we do this assessment of credibility, and this is where we are comparing the data of the OQ physical temperature mapping to our virtual model. And if we just discuss, it can also be other types of mappings, whether that's PQ. But the key here is that we are comparing to physical data, because otherwise we cannot rely on our virtual model. And then we do these seasonal variations. We mentioned worst case summer and winter to verify that it's also compliant even in other scenarios. And then finally, everything is shared with the client, and then they share that with the authorities.
Okay. So under the seasonal variations, you mentioned seasonal, but you can also simulate different levels of loading of the facility, I guess, and sort of if different impacts occur, you can sort of simulate that and forecast. Yeah.
Yeah. So
Okay.
whether you have 10% loading, 30 or 70%, and also depending on where is it loaded, it could also be that you put in a lot of warm goods into a cold store. How does that impact the neighboring goods? Are they affected by also a temperature excursion?
Okay.
So all those different scenarios you can test virtually.
So basically, you can also expand, like typically would have at a normal mapping. I think a lot of the guidelines have been developed on sort of what is feasible to actually perform. So you'd have like minimum loading, maximum loading, summer, winter, power failure, and door opening. But you could actually also simulate other risks that are quite realistic, like a temperature controlled truck coming in where the generator has gone down and now it comes with really warm goods or really cold goods.
Yeah.
So you can actually expand the sort of the scope of the testing even more.
Yes.
Yeah. Okay.
Exactly.
That's actually quite interesting.
And also you can imagine, similar to what you're mentioning, that all the goods come in at the same time.
Okay.
How does that sort of affect it? Because if we are compliant for that state, well, then we will also be compliant when only one good comes in. So it's about testing those different scenarios and then identifying what's occurring. If we then go through some of these steps, then we'd like to just show sort of the creation of the virtual model. I brought an example here of a cold store. And this is typically what you would see, where you have some racks and some goods. And we also need to implement the loggers because we later need to compare to the physical data. So there we get input from UPRI and say, we put the loggers in these corners of the racks, and then we do the same in the virtual model.
I can see someone place these in a virtual environment. I think everyone who's ever been on a ladder somewhere in a lift finds it hard, but that's what it takes.
It's much easier for me sitting with a cup of coffee and then moving some points around instead of fumbling around on a ladder. Then when we have our virtual model, we do the assessment of credibility. And here I brought an example. It's sort of a reconstruction of another project we did once. If we talk through the graph on the left, then on the horizontal axis, we have the temperature results of the loggers in the virtual model, so in our CFD model. And then on the vertical axis, we have the same loggers, but just the physical measurements. If there was a perfect correlation between the physical measurements and the virtual results, then we will see that the points would lay on the diagonal line, so the one in the middle. We never see that because there's always inaccuracies and uncertainties. But typically we see that in this case, we have about 100 lockers in the cold store that we are within plus minus 0.5 for all of them. And in case they are, and you'll see it here, one of the probes is actually outside our criteria of plus minus 0.5. So those are the lines that are just shifted away from our diagonal. And here we see that one of the probes actually exhibited that in the virtual model, it had a temperature of 5 degrees Celsius, but in the physical measurements, it was around 4.3 or 4.2. And when we then look at where was it placed in the warehouse, that is the blue probe you see on the picture on the right. And this was positioned close to the wall, and actually a little bit away from the jet. And when we then look at the data, we could see that it didn't really make sense that the probe that was the coldest in the warehouse was located close to a wall, which was facing a CRT or an ambient, so 15 to 25. You would expect that the coldest probe would be near the jet of the fan coil unit or the air handling unit that you're supplying cold air into. And then we went back to the client and we said, look, for all the other probes, we can see a good correlation. For this probe, we don't have any rationals for why it's exhibiting a different value. And then they came back to us a few weeks later and said, look, when they did the end calibration, they actually saw that there was an error in the logger.
Okay, so you actually used this to detect like calibration error.
Exactly.
Yeah, okay.
Because otherwise you would actually put up a logger in that spot and say, that would be the cold spot in my room, if that's of interest. So we need to make sure that we have rationals for if there are differences between our virtual model and our physical measurements, why that is the case.
But I can also see most of these measurements are actually really close to being where the model predicts them to be. So I guess it's also interesting to look at calibration results when trying to verify this model. Okay.
And typically the value of 0.5 degrees Celsius or plus minus, that is typically the uncertainty of the temperature logger. So your MPE or maximum permissible error. So we cannot be any more accurate than the input we get. So that's important that whatever we compare to, we can't get any more accurate than that.
Yeah, cool.
When we then verified our model, we can then explore it into some seasonal variations. So here I've shown the cold store in a worst case summer scenario. So on the left, we have sort of a histogram of the temperatures inside the cold store. In this case, we showed that our model was accurate within plus minus 0.5. So that means that if we see in the CF or virtual model that somewhere so here we are not limited to 100 loggers. We use millions and millions of loggers because you can imagine there's a logger in each of these small centicubes that we put in. And here we can see that whether we are within your 2 to 8 degree criteria. But we also need to consider that whatever we have validated, and now we are sort of extrapolating it to be in a worst case scenario, we need to have some safety factors. So that's why if we are within plus minus 0.5, then we like to add 1 degree to each end of the spectrum. So we like to be within 3 to 7 degrees Celsius. That's sort of our safety range where we have a indication that our warehouse is compliant. And then on the picture on the right, you can see that we can then get indication of where is our hotspots in the room. Is it close to any goods? If so, where is it located? And also if it changes as we go into a winter scenario, or if you have redundancy, and if you have a A/B system, how does that change? That we can check in the virtual model.
Oh yeah.
And then we have this, which is I think
CT scan.
exactly,
Yeah.
and that's what I was just about to say. It's sort of when you have broken your leg and you need to get your bone scanned.
Yeah.
We do the same for the warehouse.
Yeah.
So on the left, you see some what we call velocity, the flow field. We have high velocities when the air is exiting the fan coil units or evaporators. And then on the right, we see that we have the temperature field. And here you can sort of do your scan through the warehouse and see how the two correlates. And also, again, get your indication of here we have millions of loggers. What do each of them show?
Yeah.
So it's sort of a very advanced mapping of a warehouse.
Yeah. Yeah. Okay.
To get insights into that. And then finally, everything is documented.
Yeah.
And here we need to be really meticulous in everything we do. And we follow this guideline by the FDA. And it has some different steps we need to go through. So first you need to, of course, describe the background and what the purpose of the study is. And then step by step, you first need to verify the models you're using, the software, describe some of the system configuration. So what is your warehouse? What geometry? Is it dimensions, blueprints? Then you are tapping into sort of the mathematical equations. And then as you go along, you end up finally with either the validation. So this is where we do your assessment of credibility. And then some results and discussions. And I think here it's really key that whatever input we use, we need to have a reference for it. And we need to document and verify that whatever went as input to the model, it doesn't just come out of nowhere. To make sure that this is accurate and very detailed. So we use this approach for all the reports we do.
Yeah. But I guess also the computer models and the physics behind it, you have used in biotech a lot of years on verifying that those are actually true and that those are accepted, right?
Exactly. Yeah, for every project we do, we just gain that little more knowledge and little more insight. So that's why we can also shortcut some of the processes here, because we know what sort of ideas we have or solutions we have to some of the challenges we may face during the projects. We also touched a little on sort of the value creation of the virtual model early, and it relates to your pains that you are experiencing, because here it doesn't take us long to fill up our warehouse virtually with any goods. We can just do that in a day and within a few hours. Whereas when you do it in physical, it takes a really long time. So that's something to also know. And if we are also involved very early in the design phase, then we can you can see it as an insurance. So you have not validated your model yet, but with all the as you just discussed, we have quite a lot of experience in this area. So we use the same models every time we start a new project. And here we can then get early, when you have your early stage flow concepts and ideas, whether you will actually see compliance later.
You can sort of have a verification or some sort of assurance that the actual physical world will be within whatever range you have, I guess.
Yeah. There we can get some early indications. And I think it's also key here in some projects nowadays where things are really just over-dimensioned. And it's the person who designs it, they just want to make sure that it's compliant. And we totally understand, because of course it needs to fulfill these requirements. But then you have the site responsible
Mm.
who's paying for the electricity bill.
Yeah.
And they don't necessarily want everything to be
Mm.
within 1 degree Celsius. If you have a band of, let's say, 8 degrees Celsius,
Mm.
even with some uncertainties. So there it's important to identify that early, so we don't just put tons and tons of evaporators in a room if it's not necessary.
Yeah.
So that's also something we see where people just want to make sure they have their own sort of half to be
Yeah.
sure on that, but then the end user may have a big penalty
Yeah.
in that case. And then I think we briefly also touched upon in the beginning that when we have our virtual model, we can easily change it.
Mm.
So we don't need to sit there and be like, should I do a remapping?
Mm.
How do I expect this to change, if it actually changes anything?
Yeah.
So here you can actually back up some of your decisions with sort of scientific proof of what you're doing.
I guess also before like having to remodel a warehouse or moving shelves around or considering having in like non-conditioned goods, you can actually have a decision beforehand with relative precision that that's not going to be an issue or that might be an issue.
Exactly.
Yeah.
And that can be very beneficial. Also, if you are changing an area from, let's say it was originally designed to be a CRT, and then you're going into a cold store. Of course, you then need to verify it as you're changing the temperature criteria. But there, it's also easy to get an indication early for that.
So I guess that just a comment for that. That's often something we see where it's facilities that are being reused for a different purpose, and that has we've seen that become very costly for sure, because you don't think about the type of insulation or where doors and gates, and is the HVAC system even fully like proportionalized to the task it's going for. Yeah. Okay.
Yeah. So anything that, and that's what we of course see a lot within pharma, because the requirements are so strict. But anything where you need to be within a certain temperature range, or you also just need to make sure you don't have too much ventilation. Here, the virtual models can be really beneficial.
So I think actually I'll just bring up a question very well, and Ruhangis asks, can models also help with decreasing energy consumption then?
Yeah, exactly. Yeah. So we can then say, well, based on these still conservative heat loads and inputs in terms of the temperature outside the building, then we can tune and identify, well, what can the lowest flow rate be in the room and still achieve compliance. So you don't have the risk of non-compliance. So you can, and then you can, improve the energy consumption such that lowers as far as you can go. And we also, based on all these CT scans, we do have quite a bit of knowledge on, well, what flow concepts work well for different types of warehouses. So, for example, in a CRT or ambient warehouse, it's difficult to both heat up in the winter and also be compliant in the summer, where you are facing sort of you're opposing the buoyancy forces with the warm air going to the ceiling and the cold air going to the floor. So that's something we can also go into. Just to summarize, we then have just 3 points here on the benefits of the virtual mapping, and then later the pitfalls. We mentioned this, that we see one of the biggest gains is you can faster go live. So you don't need to use any dummy goods in order to represent a PQ state. We are also talking with a lot of clients on not necessarily doing a summer and a winter mapping, but doing a spring or fall mapping. Because as long as we just have a gradient between the room, a temperature gradient between the room and the neighboring rooms or the outside, to make sure we have a heat transfer, then we can validate our model and make sure it's accurate. So thereby you don't need to wait 3 months if you just miss the summer mapping deadline. And then we talked into these risk of non-compliance, getting early indications, and also this with the energy savings. What I think is also interesting is some of the pitfalls, because going back to my first sort of statement on colors for directors, this is typically used in some industries where it's not been validated. So, and for this application, we need to have trust in the results, and you need to make sure that it's actually been validated with physical measurements to get an indication of the accuracy of the model. So, for example, we saw in one of the projects we did that we compared our the OQ measurements to our virtual model, and there was a huge difference between the results. And we didn't really understand because the virtual model predicted that it was sort of cold near the floor of a cold store, but the physical measurements indicated that we have very warm probes. And the warmest were along the sides of the floor, so just near the concrete slab. And then we went out there and we did a site visit, and that's something we do for all the projects we do. And this is to gather input on the input to the CFD model. So we use our thermal camera to get indications of thermal leakages. And when we use that, we just saw these huge sort of sun streams of temperature or air that was warm near the floor. And that just indicated there was a thermal bridge. So air was heat was transferring through from one room to the other, and thereby heating up the probes. So that's just one example that we need to make sure that whatever we include in the model is accurate. And that also taps into sort of the garbage in and garbage out. We can never be more accurate than the input we get. Or whether when we are comparing the physical measurements, they have an uncertainty. We can never be more accurate than that. And that we need to have in mind. Yes.
Great. Thank you so much. That was truly interesting. A lot of both great questions, but also a lot of debate. I think we'll just have time for one or two questions. There's actually a great question here from Mark. What about humidity of the storage space? How can that be taken into the process?
So we do have some models on that, because that is often a requirement. Typically, you want to be below 70% in relative humidity, and that we can consider in our virtual models to see how the humidity, also when you have sources or sinks. A typical requirement in some warehouses is that the whole floor is washed or cleaned. That water will evaporate. Is that going to have an indication of or a risk of mold in the warehouse? Then we can see that in the virtual model.
Okay, so you can actually simulate the movement of liquid in the air.
Yeah. And how that dissipates the water molecules through the room.
Then I've got another question here. To be honest, it's for myself. But
yes.
When you said that you could basically do millions of probes in a warehouse, can you also simulate what the effects would be on goods inside packages, for example? Yeah.
So there we can also consider when you have your good and that is wrapped in a cardboard and maybe there's some insulation material. We have also done simulations where it's warm or a stream of air sort of goes around the good. How long does it actually take up to heat your vial or your raw product inside? Because there's some thermal inertia of the good and all the material, and that we can consider and get indication of.
Okay, that's pretty cool actually. So I think we'll have time for a very last question here. So Aaron asks, kindly elaborate why virtual temperature mapping should be done versus physical. what is the implication of performing a physical temperature mapping alone?
So I think just to get it right here, that versus the
Like
physical.
if you were only to perform a physical temperature mapping, what sort of what would the implications of that be?
So then we are tapping into some of the I think that's a great question, where the physical mapping you cannot always guarantee that you have your warmest day, and that we can in the virtual model. So there's a greater risk of non-compliance in the virtual model because you can expose it to more extreme scenarios, and then also see you're not limited to these X number of loggers. You have much more resolution in your temperature field for the virtual one.
Okay, thank you very much. I think we're going to say that's it for today. Our time is running out. Thank you so much, everyone, for the great questions along the way. And thank you very much, Joachim, for joining us here in this webinar.
Thanks for having me.
It will be possible to watch the recording online, and we'll make sure to send you a link for the webinar if you haven't seen it today, of course. Other than that, thank you very much, and thank you for attending this webinar. See you.
Thank you.